The planet Earth is unique in the solar system. It is surrounded by a blanket of gases, an atmosphere. An atmosphere that is in a finely tuned dynamic balance with the energy reaching the planet from the sun. This balance maintains remarkable atmospheric conditions near the surface of the Earth. Conditions of temperature and precipitation that allow life not only to survive, but prosper. Conditions of temperature and precipitation that over the past 10,000 years have also allowed human civilizations to develop and populations to expand to over 6 billion people. In the last half of the 20th century, scientists began understanding that human activity itself, industrialization, and the effects of this growing population were affecting the fundamental structure and composition of Earth's atmosphere. How were humans doing this? The answer was by dramatically increasing greenhouse gases in the lower atmosphere that resulted from the burning of fossil fuels. The first impact of this increase, a general warming of the planet. Other, more deadly effects are predicted to follow. It is a dangerous, rising storm. Signs of climate change brought about by global warming are everywhere. Storms are more intense, the polar sea ice is thinning and shrinking, animals such as polar bears and coral are in danger of extinction. Heat waves are more severe and last longer. These are just a few of the changes that are happening right now on our planet. Where is all of this going? Can we look into the future and see what's likely to be in store for us in the years and decades to come? I'm Bradley Whitford. Industrialization began about 250 years ago. The time since has become known as the Anthropocene era, the time during which human activity has risen to the level of a geologic force. A force capable of changing the core structure of our planet's geographic features. Its landforms, lakes and rivers, ecosystems, ocean chemistry, and the composition of the very atmosphere in which we live. The composition that determines our weather. The composition that determines temperature and precipitation. In short, the climate. This changing of the composition of the atmosphere has resulted from burning massive amounts of oil products, such as gasoline, burning massive amounts of natural gas to heat our homes and industries, and burning billions of tons of coal to heat water to generate electricity. To get some idea of how much coal is burned each year, there are more than 1,500 coal-fired power plants in the United States alone, and an estimated 6,000 more worldwide, with hundreds coming online each year. Each of these power plants has trains with fully loaded coal cars arriving from coal fields weekly and sometimes daily, and returning empty to be filled with more coal. It's an endless cycle. Coal, oil, and natural gas are fossil fuels. They are buried organic material from plants and animals that lived and died many years ago. They are primarily made up of carbon, old carbon sequestered in the earth for millions of years. And they would have stayed there for many more millions of years, except for the industrial age, when it was discovered that digging up and burning these fossil fuels produced heat. Heat energy is what is needed to power machines and heat the homes and businesses of the more than 6 billion people now living on the planet. Burning coal, oil, and natural gas chemically is combining carbon and oxygen. What you get when you do this is carbon dioxide, CO2. And it turns out that CO2 is a greenhouse gas. A greenhouse gas that once we put it into the atmosphere, stays there for thousands of years. And it also just so happens that carbon dioxide is the principal greenhouse gas that controls the delicate balance of temperatures in the troposphere, the lower part of the atmosphere where we live. The industrial age has inadvertently initiated what could be called a grandiose experiment. What would happen if much of that carbon stored in fossil fuels is converted to CO2 not over millions of years, but instead in a few hundred years? What will happen then? Basic physics tells us that the lower atmosphere must heat up, and in doing so, it must move towards a new balance point. But what does that mean? How will the effects of a warmer lower atmosphere play out for our planet's ecosystems and the 6 billion people on Earth? At the beginning of the 21st century, scientists agreed global warming was happening. But many also felt we had time to slow it down and prepare for its consequences. Now, many of those same scientists are not so sure.
So what has been occurring until now is this gradual emission and rise of atmospheric carbon dioxide as well as other greenhouse gases, which has started to change the climate. And we expect this will continue and will change climate more significantly as time goes on. It is not guaranteed, I would say it's likely, from looking at the geologic record, that the climate will not respond nice and smoothly and slowly as the forcing is. We're slowly increasing the forcing of climate change. But climate, when you look at geologic record, goes in jumps, so sudden changes. And so it would be almost a miracle if climate wouldn't respond similarly to this new forcing in a similar way by unexpected changes that are occurring rapidly.
This kind of change makes for many nightmare scenarios.
So in August, I was snorkeling in Maho, and I took a picture of this very large brain coral that I look at every time I go snorkeling there, and I saw that it was a little bit pale. And then I went back in November after the height of the bleaching, and I saw that this colony was over 90% dead. There's just a very small amount of it that was still alive. And it looked like it had been affected by the bleaching and disease. And I just remember feeling that this one really large coral colony was sort of a symbol of what all these reefs were going through, and feeling this shock that something that was probably growing when Columbus came through the Virgin Islands several hundred years ago had died in a matter of literally just a few weeks. And it also was sort of overwhelming to think that it would be hundreds of years before we would have another coral head like that.
The Arctic is warming currently, and in the Arctic are stored incredibly large amounts of carbon, organic carbon, in permafrost soils. And as the Arctic warms, the permafrost will start to thaw out, and eventually it will be oxidized. So all of that carbon, which is now preserved because it's frozen, will melt, or at least the water will melt, and then it will be, by microbes, it will be turned into CO2, adding to the CO2 burden. And it's an enormous amount. It's approximately half of the total amount of carbon dioxide in the atmosphere is locked up and could be liberated.
In as much as fire activity is connected to temperature, it appears that just the increased temperature alone is going to drive increased fire activity in parts of at least the western United States. For example, in a paper published in the fall of 2004, those projections for New Mexico, the statistical relationship suggested that in the year 2100, about 4 times more area would be burning in New Mexico than currently based upon just the temperature increase?
Well, the warming is primarily in the lower troposphere, say up to 25,000 feet. Most pronounced, say, below 15,000 feet. And it's actually cooling in the stratosphere. So if we have global warming continuing the way with the effects it has already caused, we're going to have a bigger temperature difference between the surface of the Earth and the top of the troposphere and the stratosphere. And that probably implies that the tropopause is actually going to go higher. If that happens, it would mean that thunderstorms on the average would be able to grow taller than they do today, probably by several thousand feet. And for that reason, they could be stronger than they are today.
There are very, very large deposits on the continental shelves of methane hydrates. Again, organic carbon, and it's stored currently in a zone where the temperature and the pressure are in a range that allows this to be stable. Now, as we raise the temperature of the atmosphere and the upper ocean, and therefore also of the continental shelves, that may destabilize these methane hydrates. And once they are destabilized, it may be the methane that's locked up there could be emitted, could be liberated and become methane and CO2 eventually, and make it to the atmosphere, adding to the CO2 that we have already burned from burning coal, oil and natural gas. This is something that we would have no control over, and we might be triggering this. There's more organic carbon in methane hydrates than there is in all of coal, our coal resources. The problem with that would be, it would be a positive feedback. So once it's liberated, it would cause this increased CO2 in the atmosphere, which would cause more warming, which would cause more destabilization and more liberation of these methane hydrates.
To me, the scariest thing is probably the uncertainties in what could happen. I've been doing a lot of work personally on very rapid changes in the polar climate system, and some of our models suggest that you could have very rapid changes, things changing dramatically over a decade. If those changes were to occur, the ability of societies to adapt to them would be very difficult to adapt to those very rapid, dramatic changes. And I think there's still a lot that we don't know in terms of how changes in the climate system are going to be felt at local scales, how water resources in the western United States, for example, are going to be affected. We have indications from climate models that some of those things could happen, could be quite dramatic, but there's still a lot of uncertainty. And to me personally, those uncertainties make me very nervous. I think if we knew what was going to happen, we could maybe plan better for it.
In other parts of the world, we're going to see the drying out of soil as drought, prolonged warming begins to affect the ability of those ecosystems to sustain agriculture. Freshwater systems will begin to disappear from some of these areas that are warming with prolonged droughts. I think other areas that will be impacted will be some of the Earth's tropical rainforests. They're under enormous pressure right now from encroaching development and the slash and burn in the Amazonian basin.
And ecosystems and wildlife will have even more trouble adapting, because they're going to have to do it on a very, very rapid time scale, and a lot of them aren't going to be able to keep up. And so, somebody asked me, well, so what about climate change? I said, well, okay, maybe it's not a big deal. So in 30 years, on your vacation to the tropics, there's no coral reefs to snorkel on. Does that bother you? That kind of would upset me. You see the animals that you could see in Yellowstone are now all up in northern Canada. Does that bother you that there's no more wildlife in Yellowstone? Well, these are the things that people don't think about, but those are the things that I think even modest climate changes could have big impacts on those kinds of things. Now there's more extreme things. One of the big ones lately is the destabilization of the Greenland ice sheet. And up until maybe about 10 years ago, people were thinking in terms of that the Greenland ice sheet would just slowly melt. And it would just take maybe a couple thousand years, and it would slowly kind run off into the ocean. But now there's evidence that there's these kind of rapid melting mechanisms, and one of them involves these big crevasses that open up, and as the water from the surface of the ice sheet melts, it runs down into these crevasses and gets all the way down to the surface where the ice is resting on the rock. It lubricates that surface and it starts accelerating the ice flow into the ocean.
Yeah, I think what keeps me up at night is whether or not we're really committed to maintaining our scientific focus with the investigations that we need to answer these questions. I'm not a policymaker, and I'm not kept up by questions that the policymakers have to think about. But as a scientist, I want to be sure that we are able to get people together around the world to take the measurements that we need to take to understand the problem.
Well, particularly when you look at predictions that go out 100 years, and if you, for example, say, well, humans will be smart enough to either invent technologies or do other restrictions in the emissions, even if we reduce these emissions to a reasonably small amount, the change is still going to happen. And this change is still much larger than what human civilization has ever experienced. And what keeps me up is that I'm studying climate variations of the last couple thousand years or more, where we know during this period there were climate fluctuations relatively modest in comparison to the future predictions. And during these periods, civilizations have sometimes collapsed due to climatic variations. And so if you think about this enormous magnitude of climate change that is going to happen almost by what we have put into the atmosphere already, there will be significant problems for societies that have not the capabilities of really adapting. And there are many around this planet. And of course, in nowadays world, this has connections to the rest of us as well.
It's easy to think about catastrophic changes in terms of sea level rises or temperature, that sort of thing. But I think in fact the thing that's scariest to me is the potential for social collapse. But if you look at the sort of global scale, in any given year in my lifetime, there's been 1, 2, maybe 3 kind of major environmental catastrophes happening somewhere: fires, tsunamis, droughts. As a world community, we can withstand that many disasters. We can give aid to the places that are in need of help. My sort of nightmare is what happens if you have that many disasters going on every continent every year. I'm not sure that we really have the societal capacity to buffer that, to take care of that many people in need. And that could really strain in a very frightening way our entire global social system.
So our scientists' fears and worries range from damaged ecosystems, such as coral reefs and rainforests, to regional impacts. Increased wildfires, stronger droughts, more intense and dangerous storms, and diminished water supplies. Their fears and worries also range from global collapse of world social systems to governments and people not understanding the science of global warming and not having the will to implement necessary solutions to mitigate global warming. The biggest concern, however, is the unleashing of positive feedback loops, where natural processes such as the melting of the Greenland and Antarctic ice sheets accelerate out of control. If that were to happen, Florida would disappear. New York City would be underwater. In fact, every coastal city across the globe would be wiped out. Or the melting of permafrost in the Arctic engages the heating of the atmosphere in a cascading spiral, producing a runaway greenhouse effect and turning the central United States into a barren desert. The greatest fear is that a tipping point, like this snapping of a rubber band, portends a sudden jump of the atmosphere from our present benign state to one that would destroy human civilization. This would happen if hydrous methane frozen along the ocean floor were suddenly released. 50 to 70% of all life would become extinct in a matter of 10 years. How can we know which of these fears will be realized? How can we know what will happen? What is the truth? Skeptics of human-induced climate change, or as it is now called global warming, often point to the 1970s, when climate scientists were saying the Earth was slowly moving out of the present interglacial period into a new ice age. Since the disappearance of the dinosaurs around 60 million years ago, the planet has been slowly cooling. That cooling reached a point 3 million years ago where it combined with the planet's natural cyclical wobble on its own axis to produce 4 great ice ages, a time when ice sheets a mile high extended as far south as present-day Kansas. These ice ages were punctuated by interglacial periods. The geologic record tells us that the end of the last of these interglacial periods should be happening now. Then came a surprise. In the 1980s, instead of the continued cooling of the planet, the worldwide measurements of temperature showed that the Earth was unexpectedly warming. The cooling predictions of the 70s were wrong. This was a problem. The way science deals with a problem like this is to look for an explanation. It turned out that something new had to be involved, something so powerful it could overcome the natural cycle moving the Earth toward a cooler state. That something was hypothesized to be the increased levels of carbon dioxide, a primary greenhouse gas occurring in the lower atmosphere. At the NOAA labs in Boulder, Colorado, carbon dioxide concentrations are continually being measured and analyzed. It is a practice that goes back to the 1950s.
So here's Molly Haller. She's unpacking FLAST. We get air samples from all over the world, from about 70 different places over the surface of the Earth. We get these samples in and we analyze them for greenhouse gases, in particular carbon dioxide, but also for other greenhouse gases like methane and nitrous oxide. Some of these samples are also being taken on commercial ships. There are several container ships where the crew takes samples at regular intervals, amounting to once every day or so, crossing the Pacific Ocean between California and New Zealand, Australia, or between New Zealand and Japan, and also ships crossing the Atlantic. Most of these sites we get samples from once a week, a pair of samples, so they're always taken in pairs, which is part of our quality control. If the samples are widely different, we can't analyze them. We can't do anything with the results. In the lab where they're analyzed, we very carefully measure the concentrations of carbon dioxide, methane, nitrous oxide, carbon monoxide, sulfur hexafluoride, and hydrogen gas. And we do that in a way that we are very certain that these measurements are really accurate.
When the results of these measurements are graphed against time, the results look like this, the now famous hockey stick curve of spiking CO2 concentrations. The next question was, where was the carbon dioxide coming from? Analysis of the atmospheric carbon dioxide showed that it was coming from the burning of old organic carbon, coal, oil, and natural gas. This old carbon has a distinct isotopic fingerprint. So here was something that had never happened before. The sudden dumping of carbon dioxide into the atmosphere. And atmospheric carbon dioxide does not go away for a very, very long time. Much of it just stays there and continues to build up. So new predictions based solely on the rise of carbon dioxide concentrations in the lower atmosphere were made. They stated that the Earth near the surface should slowly begin to warm up. And it has. But what does that mean? In the 21st century, the effects of this warming were playing out in surprising ways. There were thousands of stories coming in from every corner of the planet that something major was happening. More intense storms, longer fire seasons, destruction of drought-weakened temperate and northern forests from disease, towns built on permafrost sinking away, the disappearance of many of the planet's mountain glaciers, and the accelerating shrinking of the Arctic ice pack and the continental ice sheets on Greenland and Antarctica. In short, global warming was having huge and unpredictable consequences. It was clear from these global warming stories that apparently small rises in average global temperatures were accompanied by large changes in weather extremes. Regional temperature and precipitation patterns were changing rapidly, so much so that it began to scare not only the scientific community, but also the average man and woman on the street. So what's really happening? What will happen in the future? In order to answer these questions, we need to build scientific models that can reliably predict future climate changes. And as we shall see, this is a race against time. Scientific models are representations of a piece of the real world, like hurricanes, that can be used to simulate some phenomena, formulate hypotheses, and make predictions. The simplest of all models are analog models. Model trains are analog models of real-world trains. Atmospheric chemist James Roberts designed an analog model of the continental ice sheet by piling cracked ice on a piece of tar paper. He ran the model by placing the tar paper and the ice in the sun and observing the results. So an analog model can give us some ideas about how a continental ice sheet might melt, hypothesize about positive feedback loops that may come into play, and make predictions about how those feedback loops might accelerate the melting of an actual ice sheet.
We just looked at the analog model for glacial melting, and we saw that there were three feedbacks. The surface of the ice turned from white, which is reflective, to a darker color, which means that the radiation is now reaching the ground underneath and providing a warming effect and a positive feedback. We also saw that water started coming out of the ice sheet, and that provides two things. It provides means to transfer heat to other parts of the glacier, and also provides lubrication for the glacier to move and shift. And the third feedback that we saw was that the ground around the ice grew as the ice shrank, and of course the dark ground absorbs more heat than the ice does and gives us a positive feedback.
The next level of scientific model is a numerical model. The famous equations and formulas of physics are numerical models. What is important for numerical models is you need measurements. Most of us will remember from our school days the Pythagorean theorem, a squared plus b squared equals c squared. It says if you can measure the short sides of a right triangle, you can calculate the square of the long side. Here's another simple numerical model, the relationship over time to global average temperature in the 20th century. Here's another, the relationship over time to the rise of carbon dioxide concentrations in the lower atmosphere. We can combine these two simple numerical models using the same time scale, and we can see that temperature and CO2 concentrations move together. The question is, are global temperature and CO2 concentrations causally connected? The way to answer this question is to build even more complex global climate-coupled models. We will want to know more than just if increased CO2 concentrations in the lower atmosphere are causing global temperatures to rise. We will also want to know how this increased temperature will change climates, rainfall patterns, and all the other phenomena that appear to be happening. In short, what is now known as global warming. The best known computer models in this area are weather models. In order to create good weather forecasting models, we need two things. First, we need to understand the physics behind weather dynamics, and second, we need to have lots of data. Continual measurement of weather phenomena such as wind speed and direction. That's what all those tens of thousands of surface weather stations around the world are doing. They're measuring not only wind speed, but also relative humidity, that is, the amount of moisture in the air. They're measuring temperature, measuring barometric pressure, and many record the amount of precipitation that occurs during a 12-hour period, rain or snow. In the United States alone, there are over 220 weather forecasting centers, with as many as 150,000 weather reporting sources. In addition, at some weather centers on land and sea, weather balloons are launched twice a day to gather information from the upper layers of the troposphere. Finally, weather satellites send back data such as cloud cover. All of these measurements are available to the forecasters to make weather predictions.
So how do we use atmospheric observations to make a computer forecast of the weather? It's an interplay between atmospheric observations and the computer model. Now, we're able to look at the atmosphere in many different ways, by satellite from above, from surface stations, using radars. We can use wind profiles that are other kinds of radars. We've got aircraft observations. We've got this huge diversity of observations of the atmosphere. On the other side of the coin, we've got models which can give us temporal consistency, for example, a smooth evolution of the atmospheric state, and spatial consistency, relationships between what the weather is here and what the weather is 100 miles away, 500 miles away, which we can't always define as well with observations. So when we want to start a forecast with a computer, we need the best possible, most accurate description of the current state of the atmosphere. And the point is that we get it both from the measurements that we take and the computer models.
The first step for a computer weather model is to fill in the blanks, generate numbers for points in a three-dimensional global weather model, where no weather gathering stations are providing actual data. In other words, get the best possible complete description of the weather at a given moment in time. This description is called the initial state, the starting point for a weather forecast. Byron Lewis is a weather forecaster for NOAA. His job is to take this weather data, such as temperature, wind direction, and other measurements, and combine them in a way to make a weather forecast.
Just to give you an example, this, it looks like maybe a bunch of squiggly lines, but it's very important data for us. In this particular case, this is showing what's going on in the upper levels of the atmosphere as far as winds are concerned. And this is valid for Thursday at 6 p.m., Thursday evening. Now, we can put a loop on that, and you can actually watch how this pattern moves across the United States as the days progress. We can also add humidity. The area that you see that's colored indicates where the moisture is. And again, if you take a look at this, you can see how the moisture is moving across the United States as the days go on.
As we can see, all of these variables are constantly changing. They represent a highly dynamic system. That is what weather is all about, constantly changing conditions. So what are the laws that control all of this movement? Well, there are many of the well-known laws of physics, Newton's laws of motion, laws of gravity, conservation of energy, laws covering the movement of gases, the laws of thermodynamics, in all over 200 equations or laws of physics. It is into these equations that the weather data, the initial conditions, are plugged. Once plugged into the equations, then what? Then the computer does its thing. It computes what will happen next from the initial conditions and the laws of physics. The results can be displayed on a computer screen, such as a pattern of cloud formations, for example. The goal of a weather forecast is to be reasonably accurate for 3 days, and in some cases perhaps as much as 10 days. The reason weather forecasts are not more accurate is there aren't enough measurements. 150,000 weather data sources may sound like a lot, but spread over an area as big as the United States, they're a mere drop in the bucket. The reason weather forecasts are good for only a few days is because all those blanks filled in by the computer are only approximations and may contain many errors. Because weather is a chaotic system, errors compound very quickly as the weather forecast model moves forward in time. However, there is another very important use for all the weather data.
It's actually the data gathering, that's actually what creates your climate records. And every day that these observers call in these reports, that is creating the climatological database that we use today.
Indeed, all that data can be used to calculate averages for climate models. Climate models that are more complex, have different goals than weather forecast models, and are what we need to understand what the future impacts of global warming will be. In the mid-20th century, climate science was in its infancy. Empirical study of meteorological data showed that there was fairly stable distribution of climates across the planet, a distribution that produced equally stable patterns of ecosystems. Ecosystems were adapted to climate. Behind this pattern of climates is one key variable: average global temperature. Everything in climate science relates to this number and how it changes. It had been known for 100 years that the amount of solar radiation reaching the Earth each day was balanced by the same amount of energy leaving the atmosphere for outer space. Yet the lower atmosphere stayed fairly warm. The reason? Greenhouse gases. Primarily at night, greenhouse gases, in particular carbon dioxide, temporarily trapped outgoing solar radiation so the air near the surface stayed warmer at night than it would otherwise. In the 1950s, climatologists also knew that large, distinct masses of air were constantly moving across the planet in detectable patterns. For example, physics dictated that warmer air from the equator must flow to the polar regions and back to the equator. Large areas of high and low pressure moved across the globe, determining local weather. Westerly winds moved onto the North American continent from the Pacific Ocean. Trade winds had brought sailing ships from Europe to Africa to the Americas and back to Europe. Yet it was still a mystery how these large patterns of atmospheric circulation could be captured by the principles of physics and chemistry. However, it was clear that these patterns were fairly stable. The mainstream hypothesis at the time was that the atmospheric system must be self-regulating. There were times when a region did get hotter or received less precipitation, such as during the Dust Bowl days of the 1930s, but a natural correction would soon come along. It was also suggested that there were hidden natural cycles constantly producing meteorological deviations from the norm. Interestingly, against this backdrop of presumed self-regulation, climatologists knew in contradiction that past climates had been quite different. Only 25,000 years earlier, ice sheets a mile high had pushed down as far as Wisconsin. The goal of every climatologist at that time was to explain the ice ages. The key here again was average global temperature. It had changed before, and now in the mid-20th century appeared to be changing again. Attention focused on building atmospheric circulation models. By the 1950s, simple analog fluid models could produce something like the observed global circulation patterns by heating or cooling the edges of fluids. At the same time, simple numerical models using some basic equations from physics were able to reproduce circulation patterns. The problem was all these models were highly sensitive to small changes that through positive feedback loops ended up with a boiling planet like Venus or a frozen planet like Mars. Obviously, this was not actually happening here on Earth. There was, however, also a growing concern that accumulating greenhouse gases from the burning of old carbon, principally coal and oil, might produce a climate shift like the onset and disappearance of the ice ages, and that the increase of greenhouse gases alone could significantly increase average global temperature. In fact, a small change in the solar radiation balance is now occurring. Less radiation is leaving the Earth, forcing the rise in global temperature. Suddenly, climatology was not just an esoteric new science. It now needed to understand and predict future climate change. Fortunately, a new tool arrived just in time: the high-speed supercomputer. Climatologists could now combine more equations and have the computer solve them, hence produce a climate simulation. Casper Aman is one of the new breed of climatologists involved in the race to develop improved computer climate circulation models. He knows the history of the new climate science.
In the 60s, and in fact here at NCAR, several people at NCAR developed a climate model, a weather model that you would run for a much longer time than just a few days. You would run it out for a year or a decade or more. And together with Princeton, there were several groups working on, can we establish climate variations with these still very, very coarse models of atmospheric motion. But that was only atmosphere. At the same time, or later on, independent of the atmospheric models, there were models being developed for, let's say, ocean circulation. Particularly in the 70s and then in the 80s, these started to develop, and beginning in the 90s, we started to couple these two systems together. We realized we also need sea ice that changes, of course, with the seasonal cycle. And when you couple an atmosphere and an ocean, and then also the sea ice, you start to get closer to what the climate system looks like.
So atmospheric circulation is influenced by the storage and transportation of heat in the oceans. An example of this is the famous oceanic conveyor belt that moves oceanic heat in and around the continents. These oceanic heat flows are slower than atmospheric movement. An even slower physical change that affects atmospheric circulation is the shrinking and expanding of the polar ice. Snow and ice are very important because they reflect solar energy back into space. This too must be put into the atmospheric circulation model. The surface of land is not flat. For example, mountain chains rise up to 2 miles and divert airflows. One more factor that must be coupled into an atmospheric circulation model. There are even more physical processes influencing global atmospheric circulation. Hence average global temperature and weather extremes. It is hoped that the new supercomputers will soon be able to handle these. There is cloud formation.
We want to get the cloud processes a little better. The precipitation, which is very hard to simulate correctly. That's just even for present day conditions.
Another physical process that climate modelers will have to include is what happens with small particles put into the atmosphere by natural or human activities.
Another uncertainty that is always in there has to do with aerosol particles that are being emitted from humans, but also dust that is being blown off desert areas. Now these particles, when they go into the atmosphere, they're first of all complex. They're radiative interaction with the fluxes from the sun, the solar light coming down, how they reflect it or absorb, but also with heat that comes up from the surface. But it's not only this, they start to interact with clouds, and that gets really complex.
Lastly, there are the all-important biogeochemical cycles, the flows of water, methane, nitrogen, and most importantly, carbon, CO2, through the atmosphere. These cycles are all driven, in part, by life itself. All of these unrepresented processes can introduce uncertainties into the simulations of future climates as they run forward in time. Uncertainties we can no longer tolerate if we want to understand our future. What is certain is that the global average temperature in the troposphere, the air we live in, will continue to rise. The stratosphere will continue to cool. Winter in higher latitudes will be shorter and warmer. The hydrological cycle will be more energetic. And worst of all, carbon dioxide levels will continue to rise as we burn ever more fossil fuels, old carbon. The really important unanswered question is, are there positive feedback loops that can amplify this small rise in global temperature into a sudden and dramatic reorganization of climates worldwide? A reorganization that would be inhospitable to human life. There are a number of potential triggers that could do just that. Melting sea ice, melting glaciers, melting permafrost, and a change in oceanic circulation patterns. Even without these positive feedback loops coming into play, dangerous changes in weather extremes are already occurring. It is weather extremes that have the biggest impact on ecosystems, economies, and societies.
People say, well, the average climate change, a degree or two, what possible effect could that have? I mean, that's just a small change in average climate. Every day we see huge temperature fluctuations just from daytime highs to nighttime minimum that are 20 or 30 degrees. What possible difference could a warming of a couple of degrees have? Well, as it turns out, a very small change in average climate can actually have a big effect on extremes. And this is just because if you can imagine a bell-shaped curve and you're shifting the curve over into the kind of the warmer direction, the things that are happening way out in the tails are going to be exaggerated compared to the kind of the central part of of this distribution. So what this means is that the extremes are affected more dramatically than the average climate. So for small changes in average climate, you can see big changes of extremes.
Now that's exactly what's been happening in the 21st century. For example, warmer droughts are decimating whole forest ecosystems. Heat waves are killing thousands of people. And there have been a series of unusually powerful hurricanes: Ivan, Rita, Wilma, and of course, Katrina.
So this is now
Jerry Meal, senior scientist at the world-famous National Center for Atmospheric Research, has been part of a team using the most advanced ocean-atmosphere global climate-coupled models and the most powerful supercomputers to see if they can make some predictions about weather extremes. Predictions that could help us plan for future climate change. The first weather extreme they took up was very simple: the number of frost days. Frost days are when the temperature drops below freezing. The number of frost days has an impact in the mid to higher latitudes on farming, wildfires, snow cover, insect viability, and ecosystems in general.
It can affect ranges of ecosystems and wildlife. A lot of wildlife is really sensitive to when the last freeze is and when the first freeze is in the fall. So, and a frost day, of course, from the model is running and we can get daytime high and nighttime minimum out of the model as it's running, so we can actually look and count the number of days the temperatures go below freezing at night in the model, and compare that to observations where we also have those similar types of things that people have been keeping track of. So when you look at the second half of the 20th century, and you look, say, over the United States, we've seen decreases in frost days almost over the whole country, which makes sense because the average temperatures have been warming up, so you'd expect the nighttime minimum temperatures would be a little warmer, so you'd have a bit fewer nights that would go below freezing. So that seems to make sense, but the pattern is really interesting, because when you look at the pattern of changes in frost days over North America, we had bigger decreases in the western half of the country than the eastern half of the country. And these decreases of frost days going all the way up, especially up in the Pacific Northwest, have amounted to something like 15 fewer frost days now than in 1950. So that's a fairly big change and something that does have all these various impacts. So we've got this pattern, and we have observations, and we can now look at the models to see how they do. Turns out the models capture this pattern for the 20th century, and this is when we put in all these different factors that affected the climate, the volcanoes and the solar variability and the greenhouse gases and the ozone and the aerosols. The model gets this pattern of more decreases of frost days in the west compared to the east.
So now this is looking at the model projection for the end of the 21st century for changes in frost days. And we can see now this same kind of east versus west pattern that we saw in the 20th century in the observations and the model. But now this is being carried on into the future. So now we're getting bigger decreases of frost days over the western part of North America, fewer decreases of frost days over the eastern part of North America. And then we can also use the model to tell why this actually occurred. And it turns out we get a big anomalous circulation pattern such that we get more warm air being brought up from the south over this part of North America.
Encouraged by these results, the team went on to look at heat waves. Not only are temperatures getting hotter, but the frequency of heat waves was shifting from 1 or 2 a year to 2 or 3 a year. Even worse, the heat waves are lasting longer, 7 days instead of 5. What does the future hold?
Now we look at the change in this heat wave intensity in the future, and that's this bottom map over North America here. And the color scale indicates that heat wave intensity increases almost everywhere, but we've highlighted the biggest changes in heat wave intensity with kind of yellow and orange and red colors. And you can see the biggest changes in heat wave intensity are occurring in the southern U.S., upper Midwest, and over the whole western part of the U.S. So when we look at this pattern, we think that in terms of adaptation, the southern U.S. and upper Midwest is probably the best adapted for heat waves in the present-day climate, because that's where a lot of heat waves are occurring now. And same thing for the southwestern U.S., but for the Pacific Northwest, we see this big increase of heat wave intensity where we don't currently have a lot of heat waves presently, and so the impacts there would probably be somewhat different.
What about high-impact events like storms and droughts? Under the new warmer global climate, there's a shift occurring to more intense precipitation events. When it rains or snows, it rains or snows harder. These precipitation events, as it turns out, are punctuated by longer periods of dry days, consecutive days when no precipitation falls. Again, the global climate coupled model gives us a prediction about how this pattern will change across the globe.
This is a map of changes in precipitation intensity from actually an average over 9 different global coupled climate models. And if you just look over this area of North America, you can see that all the colors are kind of blues and greens, and those are all increases of precipitation intensity. And in fact, if you look globally, you can see almost everywhere there's blues and greens, indicating that almost everywhere all land areas experience increased precipitation intensity. And this is just because the warmer air can hold more moisture and you get more precipitation for a given event. But now if you look at this panel here, this is the changes in dry days. And now you can see that there's areas that are orange and red and areas that are blue and green. And the areas that are orange and red are an increase of dry days. That means there's more time in between precipitation events. There's more days where little precipitation falls. And those occur in areas where we see increased precipitation intensity. So you think, well, maybe this is kind of counterintuitive, but what happens is that when it does rain, it rains really hard, so the precipitation intensity goes up, but there's just more days in between these very hard precipitation events. So the increases of dry days can go along with increased precipitation intensity.
At last, scientists are beginning to understand how a warmer planet is going to impact ecosystems and regions across the globe. Valuable information for planning intelligently on how to adapt to climate change is within our grasp. So what's next? Will we be able to get more and better data about the climate and atmosphere and how they're changing? Will we be able to build better computer models that will give us better predictions? Will we begin to prepare now for the inevitable climate shifts before they occur? And most importantly, will we, before it's too late, move from an economy based on the burning of fossil fuels to one based on alternative forms of energy?
Given the relationships that we've seen between fossil fuel combustion, CO2 in the atmosphere, and the observed and likely future climate changes that that's causing, it's clear that we're going to need to move away from the kinds of old carbon technologies that you see in the background to more renewable sources of energy: wind, renewable carbon, and solar technologies. It's also pretty clear that there isn't one technology that's going to do the job for us. We're going to need a whole range of technologies, and we're going to need to make progress on a lot of those different fronts. What gives me hope is that as humans and as Americans, we do a good job of innovating and creating when we need to. We just need to find the political will, and we need to find the resources in ourselves to do that.
Whether the impacts from global warming are manageable or catastrophic, one thing is clear. Right now, we must move from energy sources that were appropriate to 19th century industrialization to ones suitable to the information age and for developing countries. That means an end to the burning of fossil fuels. Not only is this doable, it will challenge us to innovate in ways that will benefit all of humanity for generations to come. I'm Bradley Whitford. Thanks for watching Global Warming: The Rising Storm.